Hello everyone. This unit will demonstrate solving plane areas in polar coordinates. To solve plane areas in polar coordinates, if we will consider the first quadrant from angle 0 to angle pi over 2, and we have a curve equivalent to r as a function of theta. If we wanted to solve the area bounded from angle alpha up to angle beta, we can introduce a triangular element as it had been proven in section 109 of the book Differential and Integral Calculus by Love and Rainbit. We also can obtain an arbitrarily close approximation to the area by inscribing in it n circular sectors of radius Ri and angle delta theta. Here, the arc is equivalent to Ri delta theta. We can solve the area by taking the limit as n approaches infinity of the summation from I is equal to 1 to n of 1 half Ri squared delta theta. From the fundamental theorem, we now can say that the area is 1 half times the integral from alpha to beta of r squared d theta. Let us solve the area of a lemniscate, whose equation is r squared is equal to a squared cosine 2 theta. In algebraic geometry, a lemniscate is any of several figures that looks like the number 8 or the infinity symbol. To sketch this, we will assume values of the angle theta and solve the corresponding value of r. For instance, if theta is equal to 0, the value of r will be plus and minus a. We can plot plus and minus a in polar coordinates, where the first point here is positive a and the other point opposite it is negative a. If we assume theta to be equal to pi over 6, the value of r is plus and minus a square root of 2 over 2, and we can plot that. This is the positive a square root of 2 over 2, and opposite it is negative a square root of 2 over 2. If we assume theta to be equal to pi over 4, the corresponding value of r is 0. 0 could be plotted in the origin. It follows that if we assume values of theta, we could solve the corresponding values of r in polar coordinates. From here, we now can plot and sketch our lemniscate. To solve for the area of the lemniscate, we can introduce a circular sector element whose radius is r and the angle is the differential theta. Recalling the formula to solve for the area, which is equal to 1 half times the integral from alpha to beta of r squared d theta, we could see that from our table, at angle 0, the value of r is a, and it became 0 when the value of our angle is pi over 4. So we could say that alpha is actually 0 and beta will be pi over 4. So from the formula, replacing alpha with 0 and replacing beta with pi over 4, this is just the area of a part of the lemniscate. There are 4 equivalent and similar areas in the lemniscate. That is why we have to multiply this by 4. Why 4? Because we have 4 equal areas in the lemniscate with the limits from 0 to pi over 4. We have 4 areas like area 1, area 2, area 3, and area 4. We can now further solve by substituting the value of r squared is equal to a squared cosine 2 theta into the integrand. Substituting, we get a is equal to 1/2 times the integral from 0 to pi over 4 of a squared cosine 2 theta d theta times 4. Simplifying, we get 2a squared times the integral from 0 to pi over 4 of cosine 2 theta d theta. Integrating, we get a is equal to a squared times the sine of 2 theta with limits from 0 to pi over 4. Evaluating the limits will give us a is equal to a squared times the sine of 2 times pi over 4 minus the sine of 2 times 0. The sine of 2 pi over 4 is equal to the sine of pi over 2. The sine of pi over 2 is 1 and the sine of 0 is 0. So the final answer, the area is equal to a squared square units. Let us solve the area of a cardioid whose equation is r is equal to a times the quantity 1 plus cosine of theta. A cardioid is a heart-shaped curve traced by a point on the circumference of a circle as it rolls around another identical circle. In other words, a cardioid looks like a heart. We could plot the cardioid or sketch the cardioid by making tables. A table wherein we assume the values of theta and solve the corresponding values of r. At the same time, we can plot them now in polar coordinates. If theta is equal to 0, the r is equal to 2a. If theta is equal to pi over 6, the r is equal to 1.9 of a. If theta is equal to pi over 4, r is 1.7a. If theta is pi over 3, r is equal to 1.5 of a. If theta is pi over 2, we get an r equal to a. If theta is 2 pi over 3, the value of r is 0.5 of a. If theta is 3 pi over 4, the radius r is equal to 0.3 of a. If theta is 5 pi over 6, r is equal to 0.1 of a. If theta is equal to pi, r is equal to 0. It follows that if we assume the other sets of theta, we get the same values in the first and in the second quadrant. From here, we now can plot our cardioid. After sketching the cardioid, we can now solve for the area by introducing a circular sector element whose radius is r with a differential theta as an angle. Recalling the formula, A is equal to 1/2 times the integral from alpha to beta of r squared d theta. When theta was equal to 0, the corresponding r is equal to 2a. We can make 0 our alpha. When the value of theta was pi, the corresponding r was equivalent to 0. We can make pi our beta. So if we solve the area of the cardioid, it becomes equal to 1/2 times the integral from alpha, which now becomes 0, to beta, which now becomes pi, times r squared d theta. Take note that the limit from 0 to pi is just half of the whole cardioid. So we multiply the whole integral by 2 because there are two equivalent areas, particularly area 1 from the first and the second quadrant and area 2 from the third and the fourth quadrant. We can start to solve the area of the cardioid by substituting the value of r is equal to a times the quantity 1 plus cosine theta into the equation. Substituting, we get a is equal to 2 over 2 times the integral from 0 to pi of the quantity a times 1 plus cosine theta squared d theta. Expanding the integral, we get a is equal to a squared times the integral from 0 to pi times the quantity 1 plus 2 cosine theta plus cosine squared theta d theta. Solving further, we can use an identity for cosine squared theta to be equivalent to 1 plus cosine 2 theta over 2. Expanding the integral and at the same time substituting the identity for cosine squared theta, we get a is equal to a squared times the integral from 0 to pi d theta plus 2a squared times the integral from 0 to pi of cosine theta d theta plus a squared over 2 of the integral from 0 to pi d theta plus a squared over 2 times the integral from 0 to pi times the cosine of 2 theta d theta. Integrating, we get a is equal to a squared theta plus 2a squared sine theta plus a squared over 2 times theta plus a squared over 4 times the sine of 2 theta with limits from 0 to pi. Evaluating the limits, we get a value of 3 pi a squared over 2 square units.